All right, let's get back to our morphology and topology lecture. Last time we practiced finding 3D connected components in Fiji. That is likely one of the most useful things in general in image analysis. Image analysis and processing of scientific data. I don't think that these necessarily have to be images per se, but basically finding how many different connected components of whatever it is that I might have in my data. It's a very important exercise that is typically just part of the workflow without even being mentioned. Now, in porous media in general, these connected components could be individual particles, they could be individual fluid blobs, they could have their physical meaning. But we did have to first define what does connectivity mean in digital world. And there are some nuances there in terms of this, like 6 connectivity, 18 connectivity, 26 connectivity in 3 dimensions, and 4 and 8 in 2 dimensions. So you do have to be aware of which connectivity you're using. As long as you normalize things when you report how many components you have and all that, when you report actually total volume or normalized volume of certain class size, those results should be the least prone to huge differences in terms of which connectivity you use. Okay? So overall, let's go to that extreme example. There was that line, digitized line, that was connected only through the corners of pixels. Okay? And let's say that that line has 1,000 pixels in a row. I could either interpret it as 1,000 individual components if my connectivity is 4, or 1 component if I... So 1 and 1,000, that's a huge difference. But volume-wise, if you normalize by volume and you have a larger image, a sort of representative image, these small differences will actually, even if you counted it as 1,000 components of 1 pixel, volumetrically, that's not a lot. Okay? So it's not going to do such a huge difference when you report your values. So your report will be more robust in terms of physical meaning. So think about it. Always normalize your results in general. In general, it's always good to normalize, but in that sense, report the volumetric content of certain class size rather than the sheer number of them. Okay. Okay. So this is a plugin in Fiji that works rather well. As we pointed out, often being able to get an image of each individual component might be important if you want to do a simulation afterwards. And we will do simulation later on in this course, calculate velocity, field, and permeability. And we will basically, in that cleanup process, you want to take the largest connected component and simulate only in that, as opposed to all of the small little. So basically, if I was imposing pressure gradient or something like that, technically, physically, this would blow up because it doesn't have inlet and outlet, and if I start simulating in it, so it could numerically blow up just as well. Okay, so you don't want those things that don't contribute to overall flow. You want to remove them before the simulation. So this is again a useful tool for that. All right, so this is just a quick review of the most important concept from last time. And so in general, during segmentation, there's one way I often use to filter. You can use median filters and all other filters that I introduced, but I actually go and count when I do segmentation. After that, I kind of check the quality of my segmentation and or my image by looking at the number of these small disconnected components. If I have a whole lot of single voxel, single pixel things, I remove them. And I also double check the cumulative fraction of it because that tells you volumetrically how much they occupy. And you can see how big of an impact does your cleanup do to the porosity. And you do want to estimate that and be comfortable. We mentioned the distance labeling algorithm that was more in sort of distances in terms of integers, how many how many voxels or pixels away am I from my starting point. There is also distance labeling in PGE, which is also rather useful because it can be manipulated in all kinds of ways, and we will use it in algorithms later. So give yourself any, you can start with that bead, like just a single slice of beads or any other bead image you'd like. So let's just practice getting the distance map. So to open that image, there is plugin, process, exact Euclidean distance transform. Also, you could get a signed version of it as well. So this is not integer labeling. This is actually exact distance calculated as a real number. So you want to open. Oh, well, I have some smaller version. I'm going to resize this one. I was opening that slice, segmented slice. Its name was dry slice 150.binary. It should be in your data beads file, a data beads folder that was shared for segmentation. So just crop a rectangular section of it. Everybody knows how to do that. So you have that selection rectangle, and after you select what you want, you just do image crop. And then you get just smaller version of it. So let's just to see what works. So this image is, as I move around, it has values 0s and 255s. And then I'm going to go to process. And there's exact Euclidean and exact sign. So if you do exact Euclidean, you're going to get something like this. So for some reason, 255s here are black. Something got messed up in my
mathematical sense of the calculation of the Euclidean distance. Exactly how is the operation done in the 3D image?
It really sweeps in 4 directions. There's a fairly fast algorithm that does that. But really, what it results in is for each. So here, obviously, let's walk around the image. I have some. Whoa, my Fiji now is not happy. Okay, reopen. Let me reopen my. By leaving both installed, I asked, hey, I want both of them, and it messed something up. It created 2 versions, but actually only one of them is working, and that one has multiple things. But let me try to operate with it for now. I don't want to spend more time fixing it. Open recent. No. Doesn't remember. So it really just does pixel to pixel distance.
Pixel to pixel?
Pixel center to pixel center, there's a distance to it. Right? Mm-hmm. Okay. So here it obviously did something for these beads. And when I walk around, this image is a 32-bit image, so these are real numbers. Okay. And I can see real numbers here. Those are the actual distances. And I have zeros in the pore space. So it did something for what is phase 255. For some reason, it's inverting my LUT, or I saved it that way. So it's inverting my the way things look like. So it's showing 0 as white and 255 as black for whatever reason. So it did something just for this phase. And if you actually go and do plug-in process exact sign distance, it's going to work with both phases. It's going to have positive numbers inside 255, and it's going to have negative numbers inside pore space. Each of these numbers, so let's say that I'm in pore space or solid phase. Hey, this image is pretty. It actually gives some idea of three-dimensionality. Okay. You could look at it that way. Is it in process? There is one of them where I can actually plot it as a surface. It's one of the plugins, I believe. But so if you would plot this as a distance map on top, then I would have sort of peaks here and valleys in my pore space. Okay. And what's useful about it, and we're going to use a whole lot of it. So these distances inside the pore space, those are at every point, that distance is the largest circle in 2D I can inscribe into the pore space at that spot. Okay? If I was in 3D, it would be the largest sphere. Does that remind you of any petrophysical property? Okay. Maybe? Okay. So if I plotted distribution of those, it's somewhat similar to the pore and throat sizes, okay, together. So it's somewhat related to them. We're going to learn how to post-process the same actually distance field to actually get individual pores. Okay? But it is a very useful information to have what is the largest inscribed sphere at every spot, because we're going to use that a lot simply for estimating capillary pressure needed to enter. Okay?
This is how they do the digital MICP algorithm?
Yes, so there's, you mean the digital drainage, that type of thing? Mm-hmm. Yes, so they're working with these type of things and advancing through pore space based on these, and that's why it's actually fairly quick. You have this image is really, the algorithm underlining it is fast. It doesn't go to every pixel and find where is my nearest neighbor and then calculate. That'll be super slow. But it can do sweep. It really takes 6 sweeps through a 3D image and it's done. Yes?
So is this like the Voronoi and tessellation?
It's related to it. So Voronoi tessellation is using it as well. We're going to get to that. Okay. But this is just the distance map. And it's plain pretty. I would like a shirt with this. the design. Anyway, one of these days I'm going to print myself one. So we're going to get back to the distances, but they are useful. Okay. So let's go back to topology and using this painful Bonjour plugin. That took us a moment. So quick quiz just to remember topology issues. True or false? Donut and coffee cup have the same geometry. False. True or false? Donut and coffee cup have the same topology. True. So basically topology is something that we use in addition to geometry to describe objects. So geometrical information such as surface area, actual size and so forth are irrelevant to topology. In topology, we're going to count certain parts of this object. such as in this case number of handles. So this object has one handle, and that's something that is unique to both donut and coffee cup, and I can find continuous and differentiable transformation that transforms one to the other, and the inverse of it is continuous and differentiable, if I remember whatever topology I learned as well, and those are called homeomorphisms. Anyway, that's a little too theoretical, but let's try to take the gist, and this will sound theoretical, but ultimately it's useful, okay? So just bear with me. So the concepts are a little too topological, too theoretical. So there are three features that we're going to count. Connected components, we already did that actually. Isolated, those are these isolated blobs in my object, or number of objects. Handles, which are basically tunnels, just like that handle on the cup, or part of this donut. And cavities, which are isolated voids. And here, this is not a cavity, this is handle. But cavity would be if this was a hollow torus. There's a cavity inside. So for cavity, okay, I think about it as a sphere. It's a two-dimensional object. Okay, I need a two-dimensional surface around it to actually describe it. And I can't get around its dimensionality. Okay? Otherwise, it's called a non-bounding two-cycle, such as this hollow sphere, that I cannot, so I have a hollow part in the object, let's say like this. And basically, I cannot reduce this sphere to a point going through the object. I have to exit the object. If I have a hole, okay, I have to exit the object to reduce this sphere to a point. So if I have such a sphere, okay, then I have that hole, and I cannot reduce the object to a point through that hole. So number of holes is important, or these hollow spheres, and the fancy name for it is non-bounding two-cycle. Then the second part is these loops, or handles. They're essentially one-dimensional lines, so I can find a circle that I cannot reduce to a point, such as the circle A here, okay, without exiting the object. Okay? And then it's a little harder to find these non-binding zero cycles, or rather finding looking at them like in terms of these circles or spheres that actually reduce to themselves, but it's simply isolated components that we know how to visualize. Okay? So those are three things that we're counting in objects. Now, the numbers of each are called so-called Betti numbers. So Betti number 0 is number of connected components. We just learned how to find that. Betti number 1 is the number of handles, also known as genus. And Betti number 2 is number of cavities. Okay? So Betti number 0, 1, and 2. Now, let's try to see some of them. Okay? If I had a solid sphere, what is the number of connected components, handles, and cavities? One connected component, handles, 0, cavity, solid sphere. Hollow sphere, 1. Okay? So 1, 0, 0, 1, 0, 1. Cool. Two solid spheres. 2 connected components. How many handles? Cavities? Okay. Solid coffee mug / torus. 1 connected component, 1 handle, 0 cavity. But if I make it hollow, 1, 2, 1. So now I can actually find 2 circles that I cannot reduce to. So basically this inside acts as a handle as well. Because there's a circle, there's this circle, sort of 2 orthogonal circles that I cannot be reduced to each other and cannot be reduced to. Okay. Then solid torus, okay, I have 1 connected component, 2 handles, and now I have 0 cavities, correct. Okay. So this is, everything is the same, but there's hollow torus and solid 2 torus, this one.
hollow torus, but two hollow torus would be
Two handles, one around here,
one
cut
inside.
around here, and one here. Gets a little confusing. Now this one, okay. How many handles? I would personally say 6, but it's actually one less because they're all kind of interconnected into a network. Okay, so there's actually 5 handles. It's solid, so there are no holes, three-dimensional sort of hole. Luckily there's a formula. Where's my formula? So it's so-called Euler Characteristic. There is a whole lot of proofs in topology to prove this. This is calculated both for graphs and for objects in topology. So number of vertices, edges, and faces, which are 0, 1, and 2-dimensional elements that we actually looked at, okay, is connected via this formula. Okay, so this is something that can be worked out because I can technically digitize the object and calculate this. If I think about that digitized version of an object as a network, I can actually figure Euler characteristic, and then ultimately we're gonna do the. So Euler characteristic is both Betti number 0 minus Betti number 1 plus Betti number 2, and if I had my graph, it would be number of vertices minus edges plus faces. So let's see here. Whoops. So basically, I'm not sure why did I draw this, but basically, my number of vertices here is 1, 2, 3, 4, 5, 6, 7, 8. Number of edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So 8 minus 12 is minus 4, and plus 6, that is 2. So if I go, does that work out? 1 minus, oh, never mind. I don't have faces, they're not included. Right. So it's minus 4, so 1 minus 5 is minus 4. That they would be included if that was actually a filled sphere. Right? Fun times with topology. Okay. Now, this all sounds very abstract. But there's various algorithms. If I'm trying to thin down my object, and I probably flashed some medial axis past your eyes at the beginning of the course. Basically, if I have this 3-dimensional beast, and I'm trying to literally thin it down just like my skeleton, okay? I gain some weight, but we can remove that weight and look at just like whether my skeleton is connected, which is a good thing. I didn't break any legs, okay? So just like that, I want to actually analyze my 3-dimensional objects, especially of porous media, because they can get quite complex. So I want an algorithm that is going to maybe shave away geometry parts like extra voxels or volume, extra fat, or extra surface area, but not necessarily topology. Okay? So the connectivity of the object should remain the same. Such algorithms, we're going to get to them, are called skeletonization or medial axis algorithms. And they will preserve topology. So if I have algorithm that locally preserves this Euler characteristics and Betti numbers, as long as it knows how to count them properly, it literally goes and shakes every voxel and say, hey, can I remove this voxel without changing topology, which is Euler characteristic, basically. Okay? So as long as I think I can compute this locally, hey, can I remove it? Yes, no. If yes, remove. If no, leave it. Keep going. Okay? So that's how I'm going to thin down my object, and basically getting that thinner version of the object is useful for visualization, for search algorithms, for all kinds of things. Okay? So one could actually search for pores and throats using that type of skeleton. Now, in medical imaging also, you want to actually know to see whether you did your segmentation correctly. You imaged a physical object. I know, if all is well, that that physical object should be topologically same to a sphere. It's topologically same as sphere. Okay? So if I do the segmentation, do the representation, and do the Euler characteristic computation, it should be the same as that of a sphere. Okay? Otherwise, I have a tumor inside, I have a hole, I have a cavity. Okay? This tumor is likely a different type of tissue, so I can segment it out. So it's important for cross checks and double checks that I actually have something that I think I have. Okay? Again, so there's little things that you can play with this hole. So basically, in terms of changing Euler characteristic, drilling a hole in something, it is the same as adding a handle, which is kind of cute. But that's just for the Euler characteristic part. Now, software luckily exists, and we just hopefully installed it correctly. So let's actually get to it. So basically, if I wanted to calculate these numbers, connected components, we got that down. We know how to compute that. Cavities are actually, you count the number of connected components of the foreground. Well, let's say that it's your 255 value, and then the background, and figure out a little bit of a boundary. That can be done as well. So you can figure out how many cavities you have. And then handles are a little nasty thing, but luckily I can do Euler characteristic of this entire graph, literally voxel by voxel, and that can be, if I know the other two and I know Euler characteristic, they're connected with that Euler's equation, and we're good. Euler famously, if I remember the story correctly, in the city of, is it Leipzig? I'm gonna correct myself possibly, one of the German cities wherever he was walking, there was multiple bridges over rivers and they were connected in a network. And he figured out that rule that vertices minus edges plus faces has to be a constant number while walking around on his Sunday afternoon stroll. Okay, so I'm gonna actually dig out the story about it. Okay, so this is my Euler characteristic that I already introduced. So let's actually show how it can be useful. I'll actually show this graph after well, on Monday. Never mind. So hopefully, if you haven't, just make sure for Monday that this BoneJ plugin works, okay? And we will actually calculate these Berry numbers. And this is kind of a very useful part. And we will also look at analyzing non-weighting blobs and looking at the topology of those. Okay?